Good morning, everyone. Okay, so we will start with the problem we were solving yesterday. Okay, so just we made some mistake here, and it turns out mistake is here and here. Okay, so this should be 6. Here value should be 6. Should be 6, and this one should be 8. Divided by 3 will, so you can see like 7 times 2 divided by 3. So 14 divided by 3. So 14 divided by 3 is almost 5, right? And then 8, and then you have, this multiply this, right? 8 over 6 is 1, around 1, right? So 5 plus 1, it should be 6, so it's around 6. So 10 over 3 is wrong. Similarly, for this one, if you see 8 times 2, 16 divided by 3, around 5, right? And then you have 16 divided by 6. Yeah, so around 3. So 5 plus 3, 8. So exactly it comes 6 and 8. Yeah, and accordingly, you will get here. So you get 6, it will be 8 here, right? 6 times 8 is 48. Yeah, so accordingly, this value should be 3 over 8. So you get 3 over 8 here. Okay, and here 8, 6 here, and then 3. So you get half, right? So instead of 6, you have 2 here. Yeah, and this follows the result. This how, if you see next, this is how we found out. So U2 is 3 over 8 B naught L square over EA, and similarly U3 is B naught L square over 2. So this is what it follows. Yeah. Okay. Any question, guys? Any questions? Yeah. Okay. Okay. So let's start a new page to. Let me save it. So sometimes I lose it. So that's why. Okay. Any question, guys, so far? Okay. Okay. So so far, whatever we have done, we have seen that integration is an important part. And remember that whatever we do, it has to be done by computers. So we have seen integration is the one that we see, right? Finally, in order to find out k, we have to integrate. In order to find out f, we have to integrate. Yeah, so today we will learn the numerical methods for integration. It's also called Gauss Quadrature formula, actually. Yeah, it's also known as Gauss Legendre quadrature. Yeah. Okay, because it is related. So some coefficient that we get that comes from the Legendre polynomials, So anyway, we are not delving into the mathematics, but okay. Now, see, to begin with, we can have integration something like we can have like something like this. We have from x1 2x2, and then we will have fx and then dx, right? Okay, or you can say or let's say call it a to b, so it is better, fx dx. And this we have to find out, like typically it will be something like this, right? And finally we should be able to integrate it. And how to go about it? First, since we want to make a standard formula, what we will do, we will first convert, basically we have the x here, and yes, yeah, and it's go from a to b, yeah. From x system we can convert into a xi system, where xi goes from -1 to +1. This is the same system we are converting, yeah, we are mapping to it, yeah. So how can we do? We can say this x equal to, now when x equal to a, right, zeta equal to -1, and when x equal to b, zeta equal to 1, right? So we can map with respect to the middle point. That will be easier. So this is a plus b over 2, and here it is 0. So that way it will be easy, because we can scale it nicely, because zeta goes from here to here. So accordingly, proportional to zeta. Okay, so I think it's not zeta, it's a xi. Okay, so proportional to xi, we can map it, right? So x equal to a plus b over 2, because here it is 0. So we can write that, and plus minus whatever we can scale with respect to this one. Then plus, now b minus a is proportional to 2, right? B minus a equal to 1 is equivalent to 1 minus -1, which is equal to 2, right? So that means when we are interpolating, we can say b minus a, which is this distance. We are interpolating with respect to this one, so this is equal to 2 divided by 2, right? And then we can have xi here. So you can check, if xi equal to 0, value we get a plus b over 2, right? So we get that. When x equal to a, put x equal to a, then what happens? A minus, when x equal to a plus, you can check it, x equal to 0, we get a plus b over 2. So this is correct, because this is how it is mapped. Now x equal to a, right? Then we get a plus b over 2 plus, yeah, plus b minus a divided by 2, yeah, and then no, sorry, I'm doing something wrong. Not like that. Not x equal to a. X is a function of xi. So x equal to x as a function of xi is given like this. So x at xi equal to 0 is this, which is correct. Yeah. So this is the point in between. Now x at xi equal to -1. So a plus b over 2 plus b minus a over 2 multiplied by -1. And what do we get? We get a over 2 times a over 2 equal to a, right? X xi equal to 1, you can get a plus b over 2 plus b minus a divided by 2, right? A will cancel out, so what you have is b, right? So we are getting that, right? So this is how, yeah. So now we have to convert that into a xi system. So a to b f x dx, we want to convert into f xi system, and we can have d xi, and we can have some value here to here. Which value we want? From -1 to 1. Only thing is, we should also have something. There will be something here, what we know as a Jacobian. So we will see that. Okay, now we have x equal to a plus b over 2 plus b minus a divided by 2, and then we have xi. So dx will be equal to b minus a divided by 2, right? D xi. Right? So that means 0 to b fx dx will be equal to, what we will do? We will convert this b, f, and x as a function of xi. You can put inside it, right? And then from dx will becomes like this. So we will have b minus a divided by 2, right? Okay, and then you have d xi, and this value becomes -1 to +1, right? So
Sir,
yeah,
sir, here the limit will be a to b, na? In the last line.
yes, correct. Will a to b, so when we have -1 to +1. Yeah, so this is how we get, and finally we end up with what is equal to b minus a divided by 2, and then we have -1 to 1, and if as a function of xi it becomes, right? So we'll have a function of xi here, right? Let's call it a function b minus a over 2 -1 to 1 f xi only. So we write f xi only like that. Okay, so this not write like that. I think it's better to write g here. So this we are calling it this. Yeah. Okay. So this finally what we get, we see we are getting -1 to 1, and then this xi, then a function of xi, and then you multiply it by b minus a over 2. Yeah, that we are doing. So that means if we can solve this one in general, instead of writing g, we want to find out -1 to 1 f xi d xi, and for that we want to how to numerically integrate it. That we want to do. So how to numerically integrate. So we make it a standard, so that it is easy. We can all integration we can convert into this form, and from that it will be easy to. We have to find out a way in which this can be integrated easily. Yeah. Then how to do it? Now this Gauss formula or Gauss method, Gauss quadrature, that says that we can have this, let's say call it I is equal to -1 to 1 f xi d xi. It says that we can have a weight, yeah, wi times fxi or f xi I, yeah, where I equal to 1 to number of Gauss points. Yeah, but it says that this integration we want to do, just we should know a weight, and we should know the integration points. Yeah, so the thing is, what is the meaning of that? So let us say we have -1 to 1, we have domain, and let us say integration point, there's some concept of integration point comes into picture. And what is the meaning of that? We find out xi I. So this is xi equal to -1, here xi equal to 1. This is xi I, meaning that let us say we call it xi 0. Let's call xi 0. Yeah? Okay, now what I mean to say, we have to find out a point which can be used here. So let us say we if we have only one in Gauss points equal to only one, then our equation what we want is -1 to 1 f psi d psi, we want it as w1 multiplied by f xi1. That's it. We have to identify a point, right, where we can evaluate that function, and then we want to find out a weight that can be multiplied and we get this answer. Of course, it will not be always true, cannot find out the exact one, but depending on the order of the polynomial, we can find out, right? So, for example, let's look at example. So we can go to more mathematics, but before that, let us say our linear system. Right? If xi is linear, so we have, let us say, we have -1 here, 1 here, and this is moving like this, right? So here we have f -1, here we have f1. Yeah, so f -1 to 1, and if this is f xi which is given, then f xi d xi will be nothing but whatever you value here, this plus this. So what value we get? We get simply here this area. So it will be simply f -1 plus f1 divided by 2 multiplied by 2. So this will be simply, we get is equal to f -1 plus f1. This will be the area. What we want to find out, whether we can just evaluate at one point and we can find out, and we can indeed do it. How? By this, meaning that if we have just this, which is f0, right? So we can find out is equal to 2 times f0. What is f0? f0 is nothing but this is f0, right? So what do you get is equal, that tells you that our w1 can be 2 and xi1 can be 0, and you get the answer. And this is the exact solution, this is the exact integration you get. This is one example. Yeah. So these kind of things we are looking for, how to do it efficiently. For linear, it is easy. For others, we have to see the big picture. Yeah. Okay. So let's go further. So any questions so far, guys? Yeah. Okay. Now let's look at the general purpose function. So if xi, yeah.
Sir, so with this example, can we say that this is f0 is the integration point?
Yeah.
That equals to 0 is the integration point.
True. Okay. Exactly. Xi equal to 0 integration point, and only one point. Only one point.
Okay.
We have to extend it to multiple number of points, So, and there is a concept of in finite element software, when you work, there will be integration point things somewhere in some document it will be coming. So this is what we're talking about. There may be some kind of elements which will be called reduced integration. that really means exactly it is not calculating. So this kind of things comes from that. So let us say this is what if xi, we can have okay, let's talk about integration. So in general we are talking about I, and which is equal to -1 to 1, and then we have f xi d xi. So this is what we call I, and what we want, as I have written, so I equal to 1 to number of Gauss points or integration points, right? And then we have wi multiplied by f xi I. Yeah, so these are integration point. Xi I is the integration points. So let me also write integration points. Okay, so that will be equal to w1. We can write it like this: w1, w2, right, to wnp number gp, sorry, yeah, and then we will have f xi1, f xi2 to f xi Gauss point. Sorry, we call it ngp. So it will be ngp. Yeah. Okay. So we can, let's call this is weight matrix. So weight matrix. Yeah, and vector transpose of it, and then this is the f vector. Yeah, so let's call it this f vector like this. Yeah. Okay, now here let's expand it further. So what we will do is this one we have to find out what is the value of these guys, and we can assume a polynomial. So let's say f xi is equal to, and we can have polynomial, so it will be 1, right? We can, or not 1 but alpha naught alpha 1 x plus alpha 2x square plus, right, alpha p xp, right? And p is what is the order of polynomial, right? Yes. So what we want to do, we want to see how many Gauss points are needed in order to exactly calculate them, right? Exactly integrate them. So hence we are doing that exercise. Yeah. Okay. So f xi in general, since it will be polynomial only, as you know, that finite element we use polynomial as a solution, as a trial function. Yeah. And so in general we can write like this. Okay. So that means f xi1 is will be equal to 1, sorry, alpha naught plus alpha 1 xi1 plus alpha 2 xi2s, sorry, xi1 only, xi1 square plus alpha 3 and so on, plus alpha p xi p, sorry, xi1 to the power p, right? Similarly, f xi2 is equal to alpha naught plus alpha 2 xi2 plus, sorry guys, alpha 1 xi2 plus alpha 2 xi2 square yeah, and so on, plus alpha p xi p xi 2 only power p, and so on, right? And so on. So basically we can write f xi 1, f xi 2 to f xi ngp is equal to, and we can have a function, a matrix here, which will be alpha naught, right? So I think it's yeah. So we will have 1 xi 1 xi 1 square, so on, xi 1 to power p, 1 xi 2 xi 2 square, xi 2 to the power p, and then 1, we will have xi ngp xi ngp square, so xi ngp to power p, right? And then you will have alpha naught, right? Alpha naught, then alpha 1, alpha 2 to alpha p, right? Okay, so let's call this is equal to m and alpha, right? So what we get is this is a f, so f equal to, we call it f equal to m alpha, right? So the integration earlier we calculated equal to weight transpose of that, and then this function, right? And this is equal to weight transpose of the weight function, and f we have m alpha, right? So this is how it has to be calculated, right? So we have this m, which is coming from here, and this comes from alpha. Yeah. Now, where I is what? Where I is equal to minus 1 to 1 f xi d xi. Yeah. So this is, in general, it is like that, right? And what are we doing? We are look at this system. So finally, there are two things that we are doing. We are here, we have to find out, like we can see the example. Yeah, example n gp is equal to 2, right? And in that case, what happens? Find out the equations, what the equation tells. Yeah, so if ngp equal to 2, then we have these two equations. So we will have our I, let us say this is our I will be equal to W1 F xi 1 plus W2 F xi 2. Yeah. Okay. And looking at the, if you see the equation of okay, just a minute. I think before that, before that, we need to do one more thing, but let us say NGP equal to 2 you have. So we want I, which will be like this one. Yeah. So how many things are variable here? We have W1 you can adjust, right? Xi you can change. I mean, depending on, you have the choice, you have the flexibility, right? So you can change that. This is the variable. This also a variable. Yeah. So these are the parameters that you can change. Here also W2 is a variable. E also is a variable, right? Now, when you have NGP equal to 2, that is when you have Gauss points equal to 2, in that case, you have the 4 parameters that can be changed basically, right? Okay. And if you are saying that if xi is equal to alpha naught plus alpha 1 xi plus alpha 2 xi square and so on, alpha p xi p. Now it tells you there are 4 things that you can adjust, right? So in order to find out exactly the integration, you can go up till if xi is equal to alpha naught plus alpha 1 xi plus alpha 2 xi square plus alpha 3 xi 3. So you have degree of freedom 4. This you can change, this you can change, this you can change, this you can change. That really means that you can go till p equal to 3 in this case. Why? Because in that case you have 4 variables, 4 parameters that you can change. So this can have 4 parameters. You can also match. The exact integration will be for these 4 parameters. Why? Because in general, when we are writing xi, if xi equal to alpha naught plus alpha 1x plus alpha 2x squared to alpha p xp, then if you integrate f xi minus 1 to 1 d xi, what you get? Minus 1 to 1, and then you have alpha naught plus alpha 1, not x but xi, guys. All are these xi's. Yeah. Xi and so on. Then alpha p xi p d xi, and what do you get here? You get alpha naught xi plus alpha 1 xi square over 2 plus alpha 3. Sorry guys, alpha 1 xi alpha 2, sorry. So alpha 2 xi cube over 3 and so on plus alpha p xi p plus 1 divided by p plus 1, so on, and it will be minus 1 to 1 is equal to what? This is equal to, so we will get alpha and all we can put outside. So we can have the alpha 1 to alpha p. So actually this is the alpha vector that we defined earlier, right? So alpha 1, alpha 2, alpha 3. So this will be this alpha vector, this one. So we just write alpha in that case here, and here what do we get? We get 1 to minus 1. So it will be 2, right? So a value will be 2. Then what do you get? You get here 1 square over 2 minus 1 square over 2. So it becomes 0. So this becomes 0. Yeah. Then what do you get in this case? You get 1 over 3 and plus 1 over 3. So 2 over 3. And so on. Right? Okay. So now this is also I only, right? So we get two things. We get M, right? So previous integration, if you see, what we get? We get M alpha. So I equal to this, W transpose M alpha. So we get W transpose I equal to W transpose M alpha, which will be equal to this. Yeah. So this, let's call it P alpha. Yeah. And that tells you simply that W to power transpose M is equal to P. Yeah. So alpha is non-zero. This tells you this, and we can actually write it W1, W2 to W and P, and then you have M matrix, and M matrix looks like this guy. So 1 to this will be xi1, xi2 till to power P. So that's right, 1 xi1 xi1 square to xi1 P. Yeah, 1 xi2 square xi2p till 1, and we have xi np ngp xi ngp square xi ngp p, yeah, is equal to, we have this, we have 1 by ngp, and this is ngp by p. So here we get a matrix which will be 1 by p, right? So we'll have, so what do we get? We get here 2, 0, the way we got here, 2, 0, 2 over 3, and so on, 2 over 3, and so on, till the pth value, right? So here we got the equation. Now here we can find out basically how it works. So the first one, this multiplied by this, right? This multiplied by this has to equal to 2, right? So if ngp equal to 1, then what is the value of w? From this equation we can find out. In order to find out exact integration, how we can find out is, if ngp is equal to 1, then what happens? Our this matrix converts to what? This matrix converts to W1 only, because we have only one weight, only one integration point. So we have just W1. So we write here W1. Then next is this. NGP is only 1. So that means there will be only one row. Only one row. So we will have 1, zeta 1 squared, 2, zeta p, so zeta 1 to power p, right, is equal to what? here is equal to this, guys. Yeah, we'll have 2, 0, 2 over 3 and so on. So 2, 0, 2 over 3 and so on. Now, since we have only one point, yeah, so just a minute. No, okay, we made a mistake. So if we have like this has to be this only, sorry, right? So we are writing like this. So our number of GP is only one. So, okay, no, fine. I think one, so we have one and we have like this one, this one. Okay, so yeah, okay. So just to make sure that everything's all right. So we have NGP equal to 1. So we will have W1. Then this we will have only one. And then we have the P like this one. Okay. Now see here. If that is the case, then from first equation we get W1 equal to 2. Right? From second equation, what do we get? From the second equation, we get W1 times Xi1 is equal to 0. Right? Got it? So if first one tells you W1 equal to 2, what is the value of Xi? This tells us Xi1 equal to 0 over W1 is equal to 2, equal to 0. So Xi1 equal to 0. What is the third equation? Third equation tells that W1 Xi1 square is equal to 2 over 3. Right? So now what do we get from here? We will get Xi1 square equal to 1 over 3. So Xi1 is equal to plus minus root 1 over 3. But we cannot have, this is telling you there are, since we have only 1 points, so Xi1 cannot be 2 points, right? So in fact, the polynomial, the bigger polynomial, somewhere it is not going to, both are not, this is not consistent. So in the first case, you get Xi1 equal to 0, you have only 1 point. So Xi1 is only 1 point, but you are getting different W's, getting different Xi's, means somehow it is not, you are not getting definitely 1. That really means if you had P equal to 2, sorry, P equal to 1, right? So, if you have P equal to 1, then if P equal to 1, then what happens? Then you have exact solution you get, right? So you get everything. So what we get is, if you see here, W1, then we have 1 Xi1, right, is equal to just 2 and 0. That's it. And automatically this gives you W1 equal to 2 and Xi1 is equal to 0. Yeah, so it fits. After that, you don't have any equation, so you are consistent. You don't get any other Xi which is going to contradict this one. Yeah, so that's only, this tells you that if P equal to 1, then exact integration with only one integration point, right? And how that really tells you -1 to 1, right? F xi d xi is equal to W1 F xi 1, where W1 equal to 2, xi 1 equal to 0. As simple as that. Simple. Yeah. Similarly, in general, you can look at that equation and you can find out simply that looking at here, go back here. So we have how many parameters here? We have W1, number of Gauss points. Each of them will have two parameters, as I said earlier, right? So there will be NGP. In general, we can generalize now that NGP will have Wi's and Xi's. So two parameters meters per integration point. So 2 times NGP is the degree of freedom in a way, right? Okay. And on the other hand, you have how many parameters in this one? In polynomial. So polynomial, you have alpha 1, alpha 2, alpha 3, and so on, right? So you can generalize like this. So you have a polynomial f, right? So if you integrate, if you get -1 to 1 f xi d xi, then what do you get? You get alpha naught plus alpha 1 xi plus alpha 2 xi square over 2 plus alpha p xi p plus 1 over p plus 1, right? Sorry, the alpha 1 xi square over 2 xi e over 3 and so on, right? And you have -1 to 1. So how many parameters you have? You have p plus 1 parameters here, right? So simply tells you that p plus 1 parameters. Which one? Alpha naught, alpha 1, alpha 2, and so on. So that means you have to choose number of Gauss points such a way that this is bigger than this. For exact solution, right, 2NGP has to be greater than or equal to p plus 1, right? Or that tells you NGP greater than or equal to p plus 1 divided by 2, where p is the order of the polynomial. So if NGP is more than p plus 1 plus 2, then it will be automatically, the integration will be perfect. Otherwise, it may not. Otherwise, it will be reduced integration. Okay. Any question, guys? Okay. So similarly, we can do for NGP equal to 2. Let us see what happens. So we will have W1, W2, right? And then we will have here what? We can find out from here now that P NGP 2 NGP, right, -1. So let's see the equation. What equation we got? Here it says 2 NGP greater than or equal to p plus 1. So 2 NGP -1 should be the value of p should be. So in order to find out a p exactly, it will be p equal to 2 NGP -1. exact it can do, right? So P for exact integration, P will be 2ngp minus 1. So 2 times 2, 4 minus 1, 3. So a cubic polynomial can be exactly integrated by 2 points. Yeah, so that really means what we get here. If you see in this equation, we get 1, then you will have this will multiply to this. So we have 2 here, so we will have 2 rows only, and we will have how many columns? So P equal to 3. So 1 xi 1 2 3. So xi 1 cube till cube we will have. So we will have this. One xi 1 square, xi 1 cube, and then we will have 1 xi 2 square, xi 2 cube. So we have this is equal to, as we found out, we will have here 2 0. So we will have, so this multiply with this multiply with this multiply with this multiply with this. We should have 4 thing here. So we got 2 0 2 over 3, and there will be something else as well that we have to calculate. Yeah. So looking at it, we can find out the equation. So we have W1 plus W2 is equal to 2. These are the equation, right? Then W1 xi 1 plus W2 xi 2 is equal to 0. W1 xi 1 square plus W2 xi 2 square is equal to 2 over 3. And similarly, the last equation also will be like that. And when you solve it, yeah, when you solve it, you can find out in that case that W1 is equal to W2 is equal to 1, and then xi 1 and xi 2 is equal to plus minus root 1 over like this. Yeah. Just make guys. Yes. Okay, so that means if you have polynomial of, let us say, if you have f xi equal to alpha naught plus alpha 1 xi plus alpha 2 xi square plus alpha 3 xi cube, then you can integrate it f xi d xi minus 1 to 1 can be just done by W1 F1 F xi 1 plus W2 F xi 2, where W1 over W1 equal to W2 equal to 1, and xi 1 equal to 1 by root 3, and xi 2 is equal to minus 1 over root 3, and you can exactly you can find out the solution. The integration will be perfect, will not lose anything. Okay, rest we will see the tutorial problems. Okay, so in chapter 4, please solve tutorial problems. So tomorrow we will have chapter 4 tutorials. Okay, any question, guys? Okay, so if there is no questions, yeah.
Sir, what I'm saying is, like, we are solving differential equations by matrix method in this whole strong form we form. So,
Sure.
can we also solve the differential equation by the numerical methods also? So, sir,
Yeah.
which one is better,
Yes,
and
yes.
why are we doing by this and not by that? And which one will be better if we go for any other problem?
That differential equation that we are solving by numerical method, those are simple problems, as I told you earlier. Yeah, These problems are difficult problems.
Okay.
You got it?
Like we are right now we are just solving the one-dimensional problems, but we
Yes.
will be solving
Later on,
two-dimensional also.
you 2-dimensional, 3-dimensional. Yeah, so there it will be difficult. There will be some multi-physics also. There will be heat and a structure coupled. Lot of things will be there. So this is the differential equation that you solve. That also will take long time. So let us say you are depending on which kind of things you have. So since this is a boundary value problem, so this you can solve very fast using finite element. But if you apply those solving differential equation, you start finite difference and all, it will take ages. You follow? Finally, the differential equation that you solve, this is a kind of finite difference method basically. Yeah. Got it? So it is a numerical method. You find out what the slope is, and you try to find out df over dx is equal to you try to find out f2 minus f1 divided by b. Like that you go, and finally you find out that. But accuracy, if you see here, convergence is fast. If you take the element smaller, then you get accuracy. This is a much faster method.
Okay.
Or much, and accurate also, much accurate.
Okay. And sir, is there any case where the numerical method will be better than this? Can there be any case like that? Is it possible? I mean, is it possible?
No, it's not. This is also numerical method only. It's not something else. Okay, finite element method is also numerical method.
But
only thing
it
is
kind
this
of
may not be
Yes, sir. I'm saying like these are kind of matrices that we are solving, and like we are having very easy. It is going very easy.
No. So in differential equation, you are solving simple problems. No. When you have area is changing, E is changing, Bx is changing, then what happens then? Can you solve using your method?
No, sir. No, sir. By the numerical methods, we cannot solve them by numerical methods.
So that's why I
Sir,
told you,
I'm
this
asking
problem
like,
difficulty.
Sir, what I'm saying is like, is there any possibility that we can have the numerical methods to be better than this? Is there any possibility anywhere in the real life equation?
So this is also numerical method. I told you, this is also a numerical method. Only thing is this may not be included in your syllabus. So what you are saying, you can say some other method to solve. You can say Rangakata method, whether that is better than this method.
Yes,
that you can talk like that. But you know that there's a Rangakata method. Numerical method, only thing, which method are you studying right now? Tell me.
Sir, like
which method did you study for solving a differential equation?
Sir,
so for that simple differential equation it solves. The simple differential equation it solves. No, not like complicated like this one. Right? That is for simple, very simple equation. You solve it. Yeah. But if you want to go into more, so for that again, finite difference method. See, this is for boundary value problem, but not for initial value problem. Okay, so initial value problem you cannot solve here. So for that you have to use the differential equation method, like the one you are talking about. And for that different kind of methods are used. For that you have finite difference method. Finite difference is actually the equivalent to Rangakata only. Yeah. So, but there accuracy is a very big problem there. There may be error, a lot of error. Little bit you miss somewhere. The convergence study is much difficult in that case. Yeah. So this has other advantage. These are different advantages. For boundary value problem, you cannot beat it. Yeah.
Okay.
Boundary value problem it can solve very easily and very fast, very accurate. Yeah, but especially for linear problems. But for those cases, error may be very, very high error. So you have to do analysis of error, and it will take a long time. As you know that if you run this kind of problem, if it is a linear, so automatically you get the solution very easily, very nicely,
Yes, sir. Yes.
convert it into the matrix system. Yeah,
Hmm.
but there is no matrix system, so you go one step at a time, so it takes
Yes.
a long time. All points you have to, all time points you have to go through, all x coordinate point you have to go through, so it takes long time. Yeah,
Yes.
so
Yes.
you
Yes.
can tell that this is like a implicit method, that is explicit method. So those kind of things are comes into picture. Yeah,
Okay, sir. Okay, sir. Okay. Thank you.
got it.
Yes, sir. Yes, sir. That was
Man,
clear.
I think don't spend much time in motivation. Okay. When you study, then you will automatically have this feeling, where I can do that or where I can do it. Not wait till you understand that where I want to apply this, where I not like that. First, we study, automatically you will know that where what you can do there, what you cannot do there. So main thing is solving more problems. Yeah, then you will know the kind of problem that you can solve here, kind of problems you cannot solve there. Got it?
Okay. Yes, sir. Yes. Yes, sir.
Okay.
Thank you, sir.
Okay. Okay.
Thank you, sir.
Okay. Okay. No problem. Okay.
Sir, what would be the syllabus for the mid-semester examination?
So that will be chapter 1 to 5, chapter 2 to 5. Okay.
And sir, format will be the same like the quiz.
Yeah. It will be the same.